Okay, so we are going to start our exercise, and the exercise will consist on a voltage amplifier. So we start with our Noller implementation. It will look like this. That will be out, and then we will have R1 and R2. And we are going to load or amplify it with a capacitance here. The value of the resistors will be 20 kilo and 180 kilo ohm, and the value of that capacitance it is 1 picofarad. Let me double check. Yes, it's 1 picofarad. Okay, very good. So the first thing that we are going to do, it is we are going to calculate the asymptotic gain at low frequencies. That will be equal to R1 plus R2 divided by R1, and that is equal to 20 kilo plus 180 kilo divided by 20 kilo. 200 kilo divided by 20 kilo, that is a factor of 10. Okay, so we have our low frequency asymptotic gain. Then let's see how to actually implement this Noller. So we have our amplifier there, and we're going to implement this Noller using a differential pair here. We have the differential pair at the input, then we have the input for the two ports, looks like this, and then I mentioned that it is very common to use a current mirror load when we have a differential pair, so let's use it. So we can reuse the transconductance of both sides, so that will look like this. And then we will use second stage, and this second stage, and I will draw it like a NMOS, but in reality we will have to switch to a PMOS block due to biasing reasons, but that will come later. But I will assume that I have the connection like this. Okay, and then since I am connecting as a two port, I will have the following connection here, and then my output will be here. Okay, so this will be plus, this will be minus, this will be plus, this will be minus, and then it means that here in the intermediate node we will have to take the minus here. Okay, and the feedback looks like this. And that will be R1, that will be R2, that will be CL, V in and V out. Okay, so I have the two-stage amplifier here, and I am missing something that is important. In the current mirror there is one terminal of the current mirror that is connected here. Okay, so now it is complete. Now before going forward, let's take a look what I have done. I have implemented the nuller with the two amplifying stages like this. Okay, so this is the first stage, this is the second stage here, and then I am very careful that the output port of the first stage is connected to the input port of the first stage. So this is the input port of the second stage, this is the output port of the first stage. The other terminal of the output, it is grounded. The other terminal of the output on the second stage is also grounded, so I accomplished this. They are the same nodes. This node, it is also grounded, and my feedback goes like this. R1, R2. It comes like this, and then B in, and then I will have B out here, and then that will be plus, that will be minus, that will be minus here, convert to minus, and there will be plus again, minus here. Okay, so this is important to make sure that we are connecting the two-port networks cascaded correctly, so we don't have a violation in the connection. If we, for some reason, don't connect the output of the first stage to the input of the second stage, then our models are not correct. We will be violating the two-port assumption, and the models that we use are not correct. Then what we have to do is that we will have to replace the small signal model for the first stage and the small signal model for the second stage, and continue doing the calculations. Our first task will be to do the asymptotic feedback modeling, and for that we will add another page. So we will add a few pages that we will need. So we continue, and then we will continue, and then we will draw the small signal model for my amplifier, and then we start. We start with the voltage source here, plus V in. And then we have that for the differential pair, this will be CGS 1 divided by 2. We will have CGD, the first transconductance here, and then since this is a differential pair with a current mirror load, then we get the whole transconductance here. The whole transconductance is working. That will be V1 GM times V1, and then for the output resistance, it is only one side of the output resistance that works, so we will have RDS1, and then we will have the capacitance of only the output side that works. That will be CDS1. And that's it. That is the model for my differential pair. Now let's move forward and then let's model the second part. One terminal it is grounded. One terminal it is grounded. So we move forward, and then the second stage, it is a common source amplifier, so it is just a model of the transistor. That will be CGS2, CGD2, GM2 times, and that will be VGS2. There will be VGS2 here. Okay, and then we have this. We have RDS2, the output capacitance. We will have CDS2, and then here we will have let's draw it a bit nicely. We will have a capacitance CL, that will be our output node, and the feedback comes here like this. That will be R2. Will be R1, and basically this will be the small signal for my whole amplifier. So I'm going to mark the first stage here so it is clear. The first stage it is here, so that will be the first stage, and then let's mark with green the second stage. Second stage is here. Okay, now what we're going to do is that we're going to calculate the loop gain, and for that we are going to replace the first transconductance for a test current, and then let's just calculate the low frequencies for DC. So let's redraw the circuit. We replace the input voltage for a voltage with a 0 volt, so it is a short circuit. So that will look like this. It is a short circuit. We have this node here that is the same as here. There is a capacitor open circuit. There is another capacitor here. It is an open circuit here, going down to R1, and then from here it is going. We don't need to put it very large, and then let's see, it is going to resistor R2, and then we have a node here that goes to test current IT in parallel to RDS1. Then this one goes to BGS2, and here we have the second transconductance, and this one I keep it, I cannot just delete it. BGS2, and then I have a resistor RDS2 here. This one comes here, and this node it is grounded. Okay, so that will be my model for a small signal loop gain calculation, and then we just follow the current. So this IT will go like this. Okay, so we'll produce voltage equal to IT times RDS1. It gets converted into a voltage here, that it is minus VGS over 2. That will multiply by GM2, so that will be GM2. And then we have the current flowing here. Now we have this current flowing here, and we see that there is a current divider. Part of the current it is flowing here, and the other it is flowing through the feedback. So we are interested in the one that flows through the feedback components. So we have a current divider that will be RDS2 divided by RDS2 plus all the resistance that are in the other side. That will be R1 plus R2, and that will be this current flowing here, but I am interested in the voltage here, and that will be basically the voltage that falls over this resistance here. So I multiply this by R1, and then I get that this is going to be V1 equal. Okay, we see that the voltage here is equal to the voltage here, but with the minus sign. So we get the voltage here, and then we can calculate beta 0 is equal to V1 divided by IT, and that will be equal to minus RDS1 times GM2 times RDS2 times R1, and this divided by RDS2 plus R1 plus R2, and then we extract the low frequency loop gain. Then that will be minus GM1 GM2 times RDS1 times RDS2 times R1 divided by RDS2 plus R1 plus R2. Okay, so this will be the low frequency loop gain, and then when I give numbers to these transconductances, and for this one we are going to assume that we start already with some transistor values. So for the input transistor I'm going to use these values. The assumption at this point for this exercise is that the input transistor has already been optimized size and bias so that it accomplishes noise specifications, and the output transistor has also been optimized size and bias so that it can handle the load, so it has enough voltage swing and enough current. So we already have these values for the transconductances and capacitances, output resistances, etc. So when I give values, I plug in these values in my equation here. I get that my A beta 0, it is going to be equal to minus 1562. Okay, this is using these transistor values that I can extract using the self-CMOS script for these sizes of values and these biases here, and for the second output transistor here. Okay, so I have to check if I am right or wrong. I have to check, and then I check with the simulator, and then we switch here for a second. And in day 7 we have this the circuits here for this exercise, and then I'm going to open the X1 small signal no bias. Okay, so we'll have the following the following small signal circuit, which is exactly the same as the one that I am using in my hand calculation. A little bit later we will add the compensation network, so we can play a little bit with that. So I'm going to use exactly the same in the same way that I am using here. Now note in the lab I have another option of a small signal, and that is using the is using the small signal components that I created in lab number 1. So I just remind you that we have a small signal components also here. So I can also build the differential pair like this with these components, build my current mirror also here, build the output resistance, and even if I want, I can start adding later the biasing components that I will need. But I can use either that one or this one. There is actually, if we can use this one on this one, there shouldn't be any major difference between using two, so you can try. In the lab, I will be using this one, so you take a look that actually you can use this one. The thing that you have to be careful is that if you use these models for the transistor for the differential pair, you will be controlling the transconductance of these two devices when you calculate the asymptotic gain and the loop gain. Basically, you will be switching off both transconductance at the same time, but that is easy because you use the same parametric value here and here, so these two will be affected at the same time. But you will need a current source also that it comes from the drain of transistor 1 to this transistor here in order to inject the test current. So because that the whole combination of these two is the differential pair. So that is probably the only thing that you have to take in consideration. So you will do this during the lab. You will see this during the lab. But for now, we are going to use this one here. Okay, and okay, this is our setup, and you are already familiar with the way in which we calculate the closed loop gain, asymptotic gain, AB, and Rod locus. So I'm not going to repeat that one. So we are going to use exactly the same technique that we use there. The only thing that it is new here is maybe that I will be adding very soon the phase, so you can check also the phase margin here. So I have added the phase margin, actually the phase of AB here as an expression, and that will be this one here. We'll calculate the phase in degrees for the AB. Okay, so you can use this phase degree function from the calculator to extract the phase. So let's have a shoot here to run the simulation. Let's run the simulation and see the results. So let's take a look first. Then we have for the asymptotic gain, as we expected, we have a gain of 10. That it is exactly what we expected. Low frequencies, we get a gain of 10. That it depends only in these two resistors. Let's go to the closed loop gain, and the closed loop gain we get 9.99. So it means that yeah, it is approaching the asymptotic gain. It means that we have a lot of loop gain. It is very, very close to the ideal. We see something funny also here. that we're going to discuss very soon. This peak that we have here, it is bad news. Take a look, this is 10, and then we are peaking here at 160. When we see the position of the poles, we see that they are in the right hand side of the complex plane, and that is not good. It means that we have these poles in unstable position. This circuit will oscillate. Basically, this circuit will oscillate. And we go to the let's take a look to the loop gain. We see the loop gain, and these are the position of the poles that we're going to calculate very soon. Now let's take a look to the low frequency loop gain. So that will be, put a marker here, and it is 1562. So it is 1562. That it is exactly what we expect from our hand calculation. And we come back to our calculator here. We get that the low frequency closed loop gain should be equal to the low frequency asymptotic gain multiplied by AV null is minus 1 minus AV null, and that will be, of course, since this is so large, that will approach to 9.99 something. So it is very, very accurate due to the large loop gain. Okay, which is exactly what the simulator tells us. There is something else that we can take a look now, and it is the root locus without any stabilization. This is what we have. So let's see, like this, and then we see that the poles start here, and then they split and they go to the slowly they go to the right hand side, and they have already passed the origin. The origin is here in 0, and then become unstable. So they landed in unstable positions. So this circuit as it is going to oscillate without any compensation. It will immediately oscillate. So that is the status of the design before any compensation. So the loop gain, we are fine. The low frequency loop gain is giving us a very accurate amplifier, as we saw here in the closed loop gain. It's giving us 9.994, that it is very good, but it is oscillating. So we have to fix it. And to fix it, first we need to know where is the position of the poles and zeros. Okay, so now we are going to find those positions with the hand calculation. So poles for we are going to calculate the poles of AB, and then we are going to take first the pole at the input node. Okay, so let's take the pole at the input node. Okay, and then we need to redraw the circuit, or actually we can reuse our circuit that we have here and just add the capacitances. So let's draw the capacitance with the blue color, and then the input node depends on all the capacitance at the at the input node, and then we have the capacitance here. It is CGS divided by 2, and then we have also this capacitance here, CGD1. This is CGS1 and CD1. So note that this node, it is ground. It is ground here. It has been grounded, and this is also ground here. So actually CGS1 and divided by 2 and CGD1 are shorted. So the input pole will look like this. Then pole at the input node, we can call it this pole at the input will be equal to -1 divided by 2 pi, and then we need to find that capacitance and the resistance. The capacitance we already have, but what is the resistance that we have here? So at this node, if we redraw this circuit, it will look like this. We have CGS divided by 2. If we put this node X here, this will be ground. This will be CGD1 here, and then we will have resistor R1, and then we will have this resistance R2 here, and we will have RDS2, and okay, then going to ground, and there will be this transconductance that it is basically not working now. And so these are the this will be the poles that this will be the resistance that I am looking when I basically remove this current source here. If I remove this current source, if I remove this current source, then this one will also be removed. So these are all the resistance that I am looking now, and then I can see almost directly that this is 20 kilos, this is 180 kilos, and this is extremely large. RDS2 was a very large value. How much it was? The RDS2 was 450 kilos. So this is very large. This is very large. So most of the resistance is actually only this. So the position of my pole then will my input pole will be around R1 multiplied by, there will be CGS1 divided by 2 plus CGD1. When I run this calculation, that give me minus 209 megahertz. Okay. So let's take a look in Cadence to see if we have something around the pole. Then we go to the AB, and we have two frequencies that are low, minus 2.8 megahertz. The other it is 123 kilohertz, and this one is located in minus 231. Okay, it's 231, and then Cadence for the input pole, this has to be equal to minus 231 megahertz. So we are pretty much close, not so much error in the calculation of this pole. Probably we put these together in parallel, we will get much closer to this value. Okay, so we are happy with we found the position of this pole and where are the resistance and capacitance that depend on this pole. Then let's move to the output node. So let's see pole at the output node, and then okay, at the output node we have the following. Let's erase these ones that we don't need anymore. And we erase also this. Okay, and then we have the output node. We have all the capacitance that we have here, CDS2, and it is basically the whole capacitance, including the drain to bulk capacitance. We will have also the capacitance of the load, CL load, that is affecting this one. And then we have something very interesting here. Since we have this transconductance that it is here GM2, we have the following situation. We cannot just delete this one. There is an amplifier that it is going to be working here. So we will have to take in consideration this CGD2 here and this CGS1. Sorry, this is CGS2, and then there is the output capacitance of the first stage also that needs to be considered here. Is CDS1. Okay, because when this transconductance is not it is working, we have pole splitting. We have pole splitting, reduction of output impedance, and that affects everything. So that will affect this node, but it will also affect this node. Okay, so then we have that the output resistance, we will calculate the equivalent output resistance at the output node. That will be equal to RDS2, that it is here. And we have the pole splitting, then we have to calculate the amount of 1 over GM2 that appears in parallel, because this is the one that is reducing the resistance here. That will be equal to 1 over GM2, and then we will have also now there is this pole splitting because RDS1 it is normally a large resistance. Then we have these capacitors that are here are going to introduce a capacitor divider that basically forces the transconductance to conduct and reduce the resistance at the output. So we will have that the amount of this resistance, amount of 1 over GM that appears in parallel, it is going to be equal to this DS1, so it will be this GD2. So we will have the following expression here, and Okay, that will be the the capacitance that the resistance that we see due to the due to the transconductance here. And then we will have also that there is this resistance R2 and R1 that appear here, so that will be R1 plus R2. That is going to be our equivalent resistance here. So it is coming from RDS, it is coming from this transconductance here due to the pole splitting, and it is coming from the feedback. So these three resistance appear in parallel. And the equivalent capacitance, then we will have the capacitance at the output, that will be CDS2 plus CL, and then we have also these capacitances here. We have also these capacitors that are loading these nodes, and that will be a capacitor. We have this capacitor in series, so that will be CGD2 times CGS2 plus CDS1, and this divided by CGD2 plus CGS2 plus CDS1. Okay, and then the position of that pole will be then equal to this. So let's see if we can bring this to the next page. Very good. So, and then we have that P out will be equal to minus 1 divided by 2P, and let's change this one to out equivalent out times C equivalent out, and then the position of this pole will give me minus 2.82 megahertz, and we have to check in cadence how much it is actually. It is here, so it's one of these poles here. That will be minus 2.83. Cadence tell me that there is a pole in minus 2.83, so it has to be this one. Cadence P out is equal to minus 283 megahertz. Okay, so we have the output node, and then I will calculate also the intermediate node. So I have calculated here this will be the input node, and here will be it's including this one. This will be the output node, but we have also here the intermediate, an intermediate node here. So I will also calculate the area of the intermediate node. Then let's see here, pole at the intermediate node. So at the intermediate node, so we got that the position of the pole, it is going to be equal to -1 divided 2 pi, that will be RDS 1, and then facing all the capacitance, CDS 1 plus CGS 2 plus CGD 1 plus CGD 2, and this will be multiplied by the gain because it's a Miller capacitance, 1 divided GM2, and then by the output resistance. The output resistance at that frequency, that is the one that it is going to give the total pole position. And then we have to think this a little bit. What is the output resistance here? So the equivalent output resistance that we put for the output pole, we include the pole splitting. So this resistance here that appears due to the pole splitting, and this is important point to make. If we draw the output of the first stage, we will have RDS. We will have here CDS1. This is RDS1. We will have here CGS2, and then we will have CGD2, and then we will have the transconductance here in parallel to RDS2, GM2. Okay, so notice here that at very high frequencies, the capacitors, these capacitors here reduce the impedance and then dominate. Since RDS1 it is very large, it is these ones that are going to dominate the impedance between these nodes here. At very low frequencies, however, the capacitors have very large impedance, and we cannot disregard the presence of RDS. So I have two options here. Either I take the pole splitting resistance that I see here, that it is causing the appearance of this 1/GM multiplied by this factor, or I can disregard it and take it later if Cadence tells me that my pole is very far away. For instance, if it is at very low frequency, then that will be a very clear symptom that I have not included this part of the resistance. For now, we are going to disregard it. We are going to assume that R out, it is only RDS2 in parallel to R1 plus R2, and if this doesn't work, then we are going to go for the whole output resistance, including the pole splitting resistance that it is bring out with this factor CGD plus divided by CGD in parallel to R1 plus R2. So it will be this resistance here. So, but first let's try this one first, and then we will see the second option if it doesn't work. When I try the first option, I will get that this is giving me minus 224 kilohertz, whereas Cadence is giving me minus 193 kilohertz. So they are pretty okay. So in the script later you will see I also calculated with this one, so we will see it is not very far away either. So we keep the equation as it is. Here very quickly. So I just have the feedback, the load, the transistor sizes extracting from Cadence using our Ocean script. And I just put everything together for the first stage here. all the gate and bulk capacitance, drain to bulk and drain to source capacitance here. And I do the same for the output transistor. I put all the variables in gate to source capacitance and bulk capacitance together, and drain to source and bulk to drain to bulk capacitance together. And I just do the calculations for low frequency loop gain, and then for the positions of the poles here, all the pole positions, and then I just run my simulation here so I can calculate the poles very quickly. Now I told you that we're doing this assumption that at low frequencies there is no this splitting effect that I have if RDS is very large. I just calculated the pole, assuming that we have 1 over GM appearing in the output resistance. I mean, the assumption here is that RDS is so large in comparison to the impedance of the capacitances that I can omit it. But for that one, the pole 1 that I calculated, it has to be here. Is this one? It gives me 340 kilohertz under the assumption that I have to introduce the pole splitting. So then I leave it this one. Definitely there was at very low frequencies that resistor cannot be omitted, and then it is rendering ineffective that pole splitting at low frequencies. So low frequencies, my expression for the gain that I calculated here, it is correct. It is only RDS2 in parallel to the feedback resistors. Okay, and I come back here, and then I have a really good estimations of the poles. Then this is the low frequency pole. I will call it this one P1. The second pole, I will call this one P2, and then the high frequency pole, I will call it P3. Okay, so I have P1, P2, and P3 with very good estimations done with hand calculation.